Okay, and then let me go ahead and share this. Ooh, it's like I could barely see my full screen. There you go. Okay, so an introduction to recursion theory. In this section, we study recursive algorithm and related concepts and show how recursion ties in with induction. Illustrate how recurrence equations are used to analyze the time complexity of algorithms and study the Fibonacci sequence. I remember this one from my sophomore year, so. So an example of recursive algorithm is factorial, finding the maximum element of a sequence, computing sums in an array, and Tower of Hanoi.
Hanoi, yep.
Yeah, a true recursion needed. So in this example of factorial, consider that the factorial definition is n bang, which equals n by n minus 1 times n minus 2 times so forth, where x2, x of 1. I'm not sure if I'm reading that right.
I think it's times.
Yeah, okay, yeah. Okay, so this formula may be expressed recursively as n bang, which equals these two, what was it? How do I want to call it?
Which one? Times?
No, like this is like a formula. So like
yeah.
like if n is greater than 1, then this is the rule for it. And then if it's 1, then n equals 1 by itself. Yeah, there you go. I'm just gonna call it a rule. So like for this one, since if it is gonna be greater than 1, then n times parentheses n minus 1, they would follow this rule right here. But if it's just equal to 1, then it's 1 by itself. So in order to program and compute n of bang into a factorial n of n, if n is equals to 1, then return 1. Else, which is this first part right here of the rule, temp what equals factorial, where n minus 1, then return n times temp, and so forth. So note that this factorial problem can be solved without using recursion, but we want to start with an easy example. I mean, it was easy. Okay, so proving correctness of factorial as a recursion. So in order to prove the correctness of this recursive program may be proved by induction. So the induction base from line 1, here, let me go ahead and keep these two like that then. Okay. From line 1 right here, we can see that the function works correctly for n equals 1. So the hypothesis, suppose that the function works correctly when it is called with n, which equals sub m, for some m which is greater than or equal to 1. So we're going back to this method, which is this part of the function. So the induction step then let us prove that it also works when it is called with n, which equals n plus 1. By the hypothesis, we know that the recursive call works correctly for n equals m, and it computes n. Subsequently, it is multiplied by n equals n plus 1, thus computes n plus 1. It's just saying the same thing over again. And this is the value correctly returned by the program. Then,
okay. I think I will go over.
I'm sorry?
I think I will go over the rest.
Oh, yeah, sorry.
Okay, Towers of Hanoi. Towers of Hanoi problem. This is a two-way problem that is easily solved recursively. There are 3 towers, A, B, and C. Initially, there are n disks of varying size stacked on tower. Tower A, ordered by their size, with the largest disks in the bottom and the smallest on the top. The object of the game is to have all n disks stacked on tower B in the same order, with the largest on in the bottom. The third tower is used for temporary storage. There are 2 rules. Only one disk may be moved at a time in a restricted manner. from the top of one tower to the top of another tower. If we think of each tower as a stack, this means the moves are restricted to a pop from one stack and push in. A larger disk must never be placed on the top of a smaller disk. The recursive algorithm for moving n disks from tower A to tower B works as follows. If n equals to 1, one disk is moved from tower A to tower B. If n is greater than 1, then towers of harmony. The recursive algorithm for moving n disks from tower A to tower B works as follows. If n equals to 1, is this the same thing?
Yeah, basically, but it's like reiterating what was said right here so that since there's an example right here.
A to B works as follows. If n equals to 1, one disk is moved from tower A to tower B. If n is greater than 1, so recursively move the top n minus 1 disks from A to C. The largest disk remains on tower A by itself. Move the single disk from A to B. Recursively move back n minus 1 disks from C to B. An illustration is shown below. So for n equals to 4.
And so like this would like get moved over here. And then since you can only like move it one at a time, and then like let's say that this is C, which is the third storage. So this is just temporary storage. So the biggest value of this would stay in A so that it has like a value in there. And yeah.
Yeah, it's like a game.
Yeah, no, it's a little weird because like
Mm.
I've never heard of Towers of Hanoi. I probably did in my I don't know my earlier classes within a year, but I really don't remember it anymore. And then okay, so this is like the pseudocode for Hanoi. So
House
this should
of
be the last line.
pseudocode. Below is the recursive algorithm. The call towers ABC n moves n disks from a tower A to B using C as a temporary storage.
Mhm.
So we are using those three is shown in our picture. A, B, tower 0, tower 1, tower 2. I think yes, we can say A, B, and C, right?
Yeah.
Then towers A, B, C, then if n equals 1, move 1 A, B, then n towers A, B, C, n minus 1, move on A, B, towers C, B, A, n minus 1. Then
I'm sorry.
yeah, I don't know how to explain.
Oh, okay. So like for this one, as like it said earlier, so like
If we do it in the pseudocode, then I think we'll get the output, but right.
yeah, so like for this one, so like let's say that n does equal to 1, so you move 1 from A to B, so it returns like for this one, like let's say this one's A, this one is B, so you're gonna move this one to over here, and you're gonna be left with these three.
Yeah.
So then for towers A, C, and B, since you already took out 1 from this original 1, so you move 1 to A and B again. So then this would be on top of this one on this side of B. So then the towers would become C, B, and A. I don't know why it's like that, C, B, and A. So I'm guessing since we already used up this, we're gonna try to prove a temporary storage where we'll take out this part and move it to over here. And since this largest one has to stay on A, so you will have this part on A, and then this part on the temporary storage of tower C, and then these two would be on B.
Okay.
Yeah.
Yeah, so for the rest part we'll leave for the kids, right? From slide 9 to 13.
Yeah, 9 to 13. So 1, 2, 3, 4. Yeah, and I mean the Fibonacci was pretty easy since I already learned it from other classes. So it was just like remembering. It's just golly, I had to like type up the whole Fibonacci code one time. You had to figure out what was the problem, and it took us quite a while to figure out. So that's why I remember it. Okay, let me go ahead and stop recording.